Hello everyone, welcome to Ocean Acidification Week. Thank you for joining us for the second session, the Mediterranean OA Hub session. OA Week is presented by GOA-ON, the Global Ocean Acidification Observing Network. It's also presented by NOAA, the National Oceanic and Atmospheric Administration, the IAEA, OAICC, the International Atomic Energy Agency, Ocean Acidification International Coordination Center, and by the IOC-UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. This session will feature talks from around the Mediterranean Sea. We are glad to have over 190 registrants for today's session who are joining us from all over the world. So far, over 77 of those have already joined in, and we hope the rest will join in the next few minutes. My name is Michael Aquafreda, and I will work today as the moderator. I'm a member of the GOA-ON Secretariat, and I'm a Knaus Fellow working at NOAA Ocean Acidification Program. During the presentation, all participants are in listen-only mode. You are welcome to type any questions into the question box, which can be found at the bottom of the control panel on the right-hand side of your screen. You can also pose questions on Twitter using the hashtag OAWeek2020. When you type your questions, make sure to call out a specific person. If they're general questions, you could call out me, Michael, or if they're for a particular speaker, highlight their name so we know who to direct the question to. We'll be moderating questions throughout the session, and we'll pose them to our speakers at the end during the question and answer section, which will begin immediately after the last presentation. Today's webinar is being recorded and will be available through the GOA-ON YouTube channel soon after OA Week comes to an end. Before we hear from our speakers, I would like to share a short presentation about GOA-ON. GOA-ON is a collaborative international network designed to address three high-level goals. The first is to improve our understanding of global ocean acidification conditions. The second is to improve our understanding of ecosystem response to OA. The third is to acquire and exchange data and knowledge necessary to optimize modeling for ocean acidification and its impacts. There is a number of resources that GOA-ON offers its members, from informing policy to mentorship to providing data and hosting webinars. On the policy front, GOA-ON plays an important role at the international level. GOA-ON members assisted with the development of the SDG Indicator 14.3.1 methodology, which provides guidance on how to measure ocean acidification and how to report the collected information. This supports the UN Sustainable Development Goal 14 to build towards the 2030 Sustainability Agenda. Likewise, GOA-ON members have reviewed comments for the implementation plan for the UN Decade of Ocean Science for Sustainable Development 2021 to 2030, and also play a role in the Commonwealth Blue Charter, which has recently established an ocean acidification action plan. The peer-to-peer mentoring program pairs GOA-ON senior researchers with early career scientists to facilitate an exchange of expertise and to provide a platform for international collaborations. Through the peer-to-peer network, early career scientists are offered scholarships and trainings. The GOA-ON data portal provides access and visualization to ocean acidification data and data synthesis products, which are being collected around the world. These data come from a wide range of sources, including moorings, research cruises, and fixed time series. The newest resource that GOA-ON offers its members are GOA-ON webinars. OA Week 2020 is the kickoff to a new GOA-ON webinar series. After OA Week, webinars will continue once every 4 to 6 weeks. If you have any ideas about future webinar topics, please type them into the chat box and we'll take them into consideration as we continue planning this new exciting event. In the year 2020, GOA-ON now consists of over 750 scientists from over 100 countries. GOA-ON has 8 regional hubs, which are self-organized, and we'll be hearing from most of these hubs throughout Ocean Acidification Week. We encourage audience members to please join GOA-ON by going on to goon.org/members/join.php. One of the main reasons why we decided to host GOA-ON's Ocean Acidification Week was to commemorate the 5th International Symposium on the Oceans in a High CO2 World, which was originally scheduled to take place this week in Lima, Peru. Yet, like many other events scheduled for this year, the symposium had to be postponed due to the COVID-19 pandemic. The symposium would have brought together researchers, decision makers, and stakeholders to share cutting-edge ocean acidification science. We're really looking forward to this meeting being held in September 2021 and hope everyone listening today will visit the symposium's website and learn more. Today, we have an exciting set of speakers. But before we hear from them, I will give you a little bit more information about the Mediterranean Hub. The speakers include Patrizia Ziveri from Spain, Majd Habib from France, Marta Alvarez from Spain, Michele Gianni from Italy, Iris Hendricks from Spain, and Naira Shaltat from Egypt. To talk a little bit more about the Mediterranean OA Hub, we have the co-chair of the Mediterranean Hub, Dr. Abed El-Rahman Hassoun. I'm going to unmute Abed now, and he's going to talk a little bit about the Mediterranean Hub before we hear from our speakers. Abed, it looks like you're still on mute. Could you go over and try unmuting yourself?
Is it okay now?
Yes. Sorry about the confusion.
Okay, that's perfect. Don't worry. So I'm so glad that this session is happening now. It's amazing. So the Mediterranean Ocean Acidification Hub is one of GOA-ON regional hubs. As Mike has mentioned, it connects Mediterranean scientists who are working in ocean acidification in the Mediterranean Sea, and it is registered as a UN voluntary commitment for the ocean decade. So, so far we are 49 scientists from 10 Mediterranean countries. Why are we interested in ocean acidification in the Mediterranean Sea in general, and why are we establishing actually this hub? So the Mediterranean Sea is well known by its unique marine and coastal ecosystems that has enabled the flourishing of remarkable civilizations and a rich culture of commerce, trade, and development on its shores. However, ongoing unsustainable pressures such as overfishing, uncontrolled tourism, chemical pollution, and extensive urbanization are causing negative effects of climate change in general on marine species and the deterioration of marine important habitats. And also the increasing effects of climate change with warming temperature, with warming sea in general, ocean acidification, they are further threatening the ecological resilience of the whole Mediterranean ecosystems in general. Ignoring this puts the health, well-being, and the prosperity of the people living along the coast of the region under threat. This is why long-term strategies and decisive actions to bend the curve on nature loss is needed to protect our natural resources and secure the future of the next generations. And this is why we need a hub such this one in order to better understand ocean acidification, to better interpret what's happening in the different corners of the Mediterranean, and to communicate our findings to policymakers, stakeholders, who will ultimately take actions and strategies and put legislations maybe to protect or to do something tangible in the field. So this is why. And here in this session, actually, we have 6 speakers, as Mike has mentioned, and this will give us the opportunity to learn more about ocean acidification latest updates in the area. Thank you all for being here. And now I'll give the floor to our first speaker, Patrizia Ziveri. The floor is yours.
Patrizia, I just made you the presenter, so you could go ahead and share your screen whenever you're ready. I'm going to ask the other panelists to please stop sharing your screen until it's your time to speak. This just helps with some bandwidth issues that might crop up. Thank you very much. Patrizia, you'll also have to unmute yourself. Patrizia, we're seeing your screen, but we're not seeing your presentation. We're seeing a beautiful picture of the what I think is the Spanish countryside. Maybe the Italian one, who knows? All right, now we're seeing your screen. Just go ahead and unmute yourself. At the top, there's the microphone button.
Okay.
I think we could hear you now.
Okay, can you hear me now?
Yes. We're
Yes?
ready to go.
Okay.
Yep, we could see your slides and you could take it away. Thank you.
Oh, thanks. So first of all, I would like to acknowledge the organizer of this Ocean Acidification Week, and I'm really pleased to be here and give this first presentation in this Mediterranean session. So I would like to acknowledge the Global Ocean Acidification Observing Network, the Ocean Acidification International Coordination Center, the IOC and NOAA, and also, of course, the Mediterranean Hub. So I also like to mention my co-authors, Michael Grelot and Jacob Parker, that helped me to put together these data synthesis. So a large number of publications has been actually published in the last 20 years or so, and this presentation here, the short presentation, want to give a short overview about this data synthesis, considering the different key topics like chemistry, biology, and socioeconomy. Also, we go through quickly about who is doing the research, and also possibly main outcome and next steps, and hopefully we have time at the end in the discussion panel to discuss these next steps. So this is the first presentation in this Mediterranean session. I wanted to highlight the importance of this region for ocean acidification studies. Abed already mentioned the societal importance of this region, but it's also scientifically it's very exciting to work here, because this small-scale ocean has very fast overturning circulation in the order of 80 to 100 years. For example, in the Western Mediterranean, the deep water actually are renewed every 20, 40 years. So it's a very dynamic ocean, or small ocean, and also is a warming fast, this ocean, and is evaporating with the high saline water. So it's affecting an important parameter, this Revel factor, that is low Revel factor, so it has the capacity to absorb large amount of CO2, including, of course, large amount of anthropogenic carbon. And what you see here is a simulation done by James Orr, is one of the products of this project that I will mention later, the MEDSEA project. And it's a simulation of omega aragonite state for Mediterranean from the pre-industrial time to the end of the century, and you see the propagation of basically acidification in the basin. And on the right side here, you see a panel. So it's basically a transect from the Gibraltar Strait to the Levantine Basin, so the Eastern Mediterranean. And you see also the Sicily Strait, and you see all the different water masses with different characteristics and also different rate of change in terms of pH. And I will touch this topic later. So as mentioned, we are doing this meta-analysis. It's a work in progress, and so we are doing this bibliographic database based on the IAEA Ocean Acidification International Coordination Center database. We are also using other databases like, for example, the Web of Science, but most of the work that I'm showing here is from this database. And we are using the preferred reporting items for systematic reviews and meta-analysis, PRISMA, and also we are using very specific criteria for distinguishing the publications, and we are considering the publication from the last 20 years, so from 1999 to today. So this is the first plot I want to show you in terms of publication records. This is the annual number of peer-reviewed publication on ocean acidifications. I cannot use my cursor, so I cannot really indicate it, sorry. But you see here on the right side, you see the record and the line with for the general ocean acidification, so the number of publications. And as you probably have seen already in this plot, you see this rapid growing knowledge in terms of research output since the mid of 2000. And for the Mediterranean research outputs, you see that it's really starting basically in the last, since the last 10 years. So more or less from 2011, you really have this increase in publication record that is evident from this plot. And when you look a bit more in details and you look at the type of publication, you really see that the dominant topics and publishing in OA is really the biological type of publications. So publication dealing with the species-specific response of Mediterranean organism to acidification done mainly in laboratory experiment. Also in the Mediterranean, it's quite known that there are CO2 vents. So there are many publications also done using this natural laboratory of CO2 vents. And secondarily, we have some mesocosm experiment, also time series and surveys. And then the other type of publication that we have quite through the time interval is the publication there with the carbonate system of the Mediterranean. Only very secondary and minor contribution is done by the paper dealing with the societal impact or socioeconomic impact, and then very few on Mediterranean review. Also wanted to mention from these figures that it's important to note that there are two major initiatives that they were done in this time period. The one was the very first coordinated large European project on ocean acidifications, EPOCA, that started in 2008 and ended in 2012. And in this project, there was a small contribution also on the Mediterranean research, but I would say that most of the contribution has been, at least the beginning of our knowledge of ocean acidification in the Mediterranean was really stimulated by this other project, European coordinated project, Mediterranean Sea Acidification in a Changing Climate, that really stimulated the science and the knowledge in the area. We calculated about 65% of publication, at least from 2011 to 2013, were actually contributing to, were actually linked to this initiative. So we analyzed almost 400 papers, 376 papers, and 78% were dealing with biological response, I mentioned, and 16 with the carbonate system. You really see this big contribution in terms of research output since the last 10 years, since 2011, and then I didn't comment on this, but you see a slight deflection in terms of research output publications since 2017. Also wanted to mention where this research is done. This is still in progress. We still have to scan more papers, but in general, the figures here is showing that most of the publication output is coming from 3 countries, that is Italy, France, and Spain. And for the Eastern Mediterranean, so there are many European countries. For the Eastern Mediterranean, where we look at the Levantine Basin, the most important non-European countries that are published are Lebanon and Israel. But then a main message from these figures is that there is basically a lack of research output and probably also research in North Africa. That is really a strategic place. It is really much linked also to Mediterranean and also to in the Balkans and in general also in the Eastern Mediterranean. If I have time, I'll go back to this a bit later in my last comments. Another interesting point that I also mentioned at the beginning was when I showed this transect from the Gibraltar to the from the Atlantic influx of water in the Mediterranean to the Levantine Basin. There are these different water masses, and there have been several papers that are now trying to estimate the delta pH, so the contemporary delta pH per year. And in the Western Mediterranean, this delta pH that has been derived from time series, unfortunately quite short time series in most of the cases. The longest one are in the Ligurian Sea of France, but it's quite consistent. It's from 0.02 to 0.03 units per year. And in the Eastern Mediterranean, we have one paper that has been published of Lebanon, and is showing like this possible larger range in changes in terms of delta pH. There's still a need, I think, of more studying, understanding better the delta pH, particularly when we are dealing with the deep water masses in the Mediterranean. Then in summary, we mentioned we scan and this almost 400 papers in the Mediterranean, so there is quite a significant amount of research that already been done, and a lot of knowledge has been created in terms of acidification impact and acidification dynamics in the Mediterranean. But I would say that it's quite obvious that even if it's becoming less and less biased toward Western Europe and Western Mediterranean, there still need to emphasize that the non-European researcher institution involvement has to be improved. Also in terms of geochemical studies or chemical study, I didn't touch this topic. This is about anthropogenic carbon, but there's still quite a range in anthropogenic carbon estimate. All papers published, they are highlighting the high concentration of anthropogenic carbon, and there is a range between 40 to 100 micromole of kilo per in the Mediterranean waters. However, there's not really a common ground yet between using the different methods for estimating anthropogenic carbon. And I already mentioned about the delta pH falling quite consistently in the Western Mediterranean, and for the Eastern Mediterranean, the range seems higher. In terms of biological impact, there is really a large number of papers on biological impact on Mediterranean species, but I would say that a lot of work has been done in the northwestern Mediterranean Sea, but so we need more spatial diversity needed, probably also more surveys, and we need more study at the ecosystem levels, and transgenerational study also to address physiological plasticity and try to understand a bit more what we wanted to understand, that is also the adaptations of endemic species or keystone species in the Mediterranean. Finally, in terms of socioeconomic studies, there is still a lack of knowledge related to the socioeconomic impact. We started this in the MEDSI initiative, and there was even a framework, but it's not been very much applied. One is, so there is really limited understanding about the potential impact in many regions, including North Africa, Eastern Med, and Balkan. And finally, I think we really need probably a third generation of research program, more networking with European and non-European countries in the Mediterranean. I think is really key. And probably the focus should be a bit less Eurocentric, and also the study should be more transgenerational experiment, and also quantification ecosystem scale changes, and more also linking societal need with the scientific knowledge of acidification. So thank you.
Thank you so much, Patrizia. That was a really great presentation. I'm going to pass it over now to our next speaker, Majd. All right, Majd, you'll just have to unmute yourself, but we can see your screen.
Hi. Good morning.
We can hear you loud and clear, and your presentation looks good. You can take it away.
Good morning. Before I start, I want to thank the organizer of this seminar. Also, I want to thank my two teams at CEREGE Lab in France and the CNRS Lebanon that this work is done in collaboration between the two. In my short presentation, I will talk about these points: introduction, methodology, objective, preliminary results I have obtained until now, and the conclusion. The semi-enclosed Mediterranean Sea is very vulnerable to environmental changes and anthropogenic pressures. Nowadays, human activities are perturbating the atmosphere by the excessive amount of CO2 released. In retrospect, the ocean is the reservoir of CO2 in which is a large portion of carbon dioxide. All these changes will lead to three processes, which are ocean acidification, deoxygenation, and warming, where these phenomena will impact the base of the marine chain, namely the phytoplankton population, such as coccolithophores. What are coccolithophores? Coccolithophores are known since 1900s and are till now under intensive care from the scientists, since they are very important in our ecosystem. They are calcifying tectonic species that are behind the major part of the production of more oceanic carbonates. These species play a key role in the modern oceanic biogeochemistry and in sequestering organic matter into the bottom of the sea. The objective of my work is to study how these calcifying phytoplankton populations, such as coccolithophores, react to biogeochemical changes connected to global phenomena such as ocean acidification and to local such as pollution. The study area is in Lebanon, eastern of the Mediterranean Sea, and in Marseille, in France, the western of the Mediterranean Sea. I chose these two areas because in the eastern of the Mediterranean, we have lack of studies concerning this topic. Whereas in the western part, we have many studies about it, so we can compare between the two. As you can see in these, we use the NISCM bottle in order to take the water samples from different depths, and we filtrate them in cellulose nitrate membrane. To observe our results, we observe them using the optical microscope and the scanning electron microscope. So we use the optical microscope in order to measure the mass and the thickness of each cocosphere, also to know the abundance of coccolithophores. For the scanning electron microscope, to study the taxonomy and to check for any abnormalities in the cocospheres. Here, as a preliminary results for the biodiversity of cocospheres, we have obtained 31 species of coccolithophores in 15 samples from 2018 until 2019, where similar to the ones obtained in other Mediterranean areas. These pictures are some of the species that I have obtained using the scanning electron microscope, where the most and dominant species is the first one, Emiliania huxleyi, and other species I have obtained in Lebanon sampling during 1 year. For the hydrographic parameters in Lebanon, here we have the variation of temperature and salinity with respect to depth in each season, where the highest temperature and salinity was recorded because of high evaporation rate, and the lowest temperature was in spring because of snowing and river discharges, and for the salinity, the lowest was in summer. For the biogeochemical indicators, also in Lebanon, here we have the variation of pH and dissolved oxygen with respect to depths, also in each season. So the maximum was in summer, the pH, the minimum was in summer, and the maximum was winter, where the pH ranges between 7.8 and 8.24. Where the maximum was in summer because high evaporation rate, as I said before. For the dissolved oxygen, as we go down with depth, the dissolved oxygen increases. Here is an analysis for Emiliania huxleyi cocosphere in Lebanon. We have the variation of mass of mass and thickness of sphere with respect to season, where the highest mass was 13 picograms and the minimum was 17.5. The maximum was, as you can see, in fall, and the minimum was in summer. And the thickness was the minimum 0.59 and micrometers, and the maximum was 0.71 micrometer. So here, just to see if there is any effect of pH, in other words, ocean acidification of cocosphere. We have the preliminary results. Until now, we can see as the pH decreases, or the cocosphere decreases too. Also, more drivers or parameters such as total alkaline or carbonate parameters in general should be analyzed to assess any potential correlation. In the analysis of Emiliano-Huxley cocosphere in France, since from 2014 until today, we have now the variation and thickness of cocosphere with season, where the maximum was in winter recorded 26.33 picograms, and the minimum was 21.51 picogram in summer. For the thickness, the maximum was 0.65 micrometer, and the minimum and the maximum was 0.74 micrometer. Here is a quick comparison between Lebanon and France samples. As you can see, the range of the mass of cocosphere in Lebanon is larger than the range, also for the thickness. And the maximum mass was recorded in Lebanon, whereas the opposite for the thickness, the maximum thickness was recorded in France. This can be attributed to different carbonate system characteristics in the two areas, in the east and the western of the Mediterranean. More data should be analyzed in order to interpret these results. Finally, as a conclusion, these results are obtained for the first time in Lebanon, Eastern Mediterranean Sea. More chemistry parameters are collected to study the ocean acidification effect of coccolithophores and to check for any potential correlation, as I said before. Also, the sediment samples are already taken and will be analyzed, and this will help us to better assess the past response of coccolithophores toward ocean acidification. Therefore, we can easily predict the effect of ocean acidification on coccolithophores in the future. Thank you so much for your attention.
Thank you so much for that, Majd. Next up, we have Marta. Marta, I've gone ahead and made you the presenter. You'll have to just unmute yourself.
Okay. It's working now.
Yes. We see your desktop.
Okay,
if you want to just pull up your PowerPoint.
Okay. Is it working?
Yes. Why don't you just put it in full screen mode, and then you could begin.
Okay.
That looks great.
Good morning, everybody. Okay. Wait. Good morning, everybody. This is Marta Alvarez from lovely Galicia in the northwest of Spain. I would like to thank the organizers for inviting me to contribute to this hub. You know that the time series for carbon are precious because we want to understand any changes in the physical and biological carbon pump in the ocean, especially in those areas more sensitive, like for example, the Mediterranean Sea. So some years ago, we started to work in collecting data from different cruises in the Mediterranean Sea. The Mediterranean Sea, as you know, is considered a laboratory basin because it suffers a high anthropogenic pressure. It is a closed, practically closed marginal sea, just open to the North Atlantic through the Gibraltar Strait, and it is a
wide sea and quite deep, with a mean depth of 1,500 meters. It is completely surrounded by different countries with a high population near the coast and an active industry and tourist activity there. So it is considered a kind of mini ocean because all the typical ocean processes occur in a much smaller and shorter spatial and temporal scale. But any changes in the Mediterranean Sea could contribute to changes in a wide area as the open North Atlantic Ocean because of the contribution of the Mediterranean overflow water through the Strait of Gibraltar, affecting the formation of North Atlantic deep water and also directly directly linked to the central waters in the eastern North Atlantic. In addition, it has several sites for deep water formation, both in the eastern and in the western Mediterranean Sea. So physical changes in the circulation and ventilation of the water masses have already, have already happened. For example, in the 90s, the deep water formation site from the Adriatic Sea changed to the Cretan Sea. This is called the Eastern Mediterranean transient. And as well in the Western Mediterranean, we have changes in the bottom and deep waters. They are becoming more saltier and warmer. This is called the Western Mediterranean transient. And what happens to the biogeochemistry? There is no deoxygenation threat for the whole basin because deep waters convey oxygen to depth, and there is an increase in the input of nutrients, like you can see here in these plots, because of human activities, and this could have a likely impact in ocean biogeochemistry, in ocean productivity. What about the anthropogenic carbon? This marginal sea, as you have heard, is actively ventilated every year. So the carbon uptaking in the surface can be conveyed to depth. So it has a very high specific anthropogenic carbon inventory, as you can see here in this table, and for example, in this global plot of the inventory of anthropogenic carbon. As Patrizia explained, this is because of the chemistry, very specific chemistry, carbon chemistry in the Mediterranean Sea with a low Revel factor, a high alkalinity to DIC ratio, which helps the ocean to really follow more easily the increase of CO2 in the atmosphere. But the impact in pH is lower than for example, in the North Atlantic. In addition, the Mediterranean Sea is also receiving anthropogenic carbon from the adjacent North Atlantic. So when we want to talk about the budgets of carbon, we need to know not only the air sea, but also the storage and the transport in the different subbasins. This anthropogenic carbon leads to ocean acidification, but there are, as also Patrizia commented, there are different estimates for the anthropogenic carbon because it's an estimate, not a measure, and consequently there are different numbers for the final decrease in pH. Another way of getting the number for the reduction in pH is, of course, data, temporal time, sustained time series. I don't have a map for those, but there are different time series, quite recent, unfortunately. I think the eldest is the DIFAMET in the Gulf of Lyon since 1995. And yeah, So CARIMED wants to gather data from the carbon data from different cruises in the Mediterranean Sea, because there is a lack of easily findable and accessible and public carbon data in this basin. So we want to create a merged, consistent, calibrated, and homogeneous and public database collecting historic and recent subsurface measurements of carbon variables, pH, alkalinity, and DIC, as well transient tracers like chlorofluorocarbons, helium and tritium, and sulfur hexafluoride. And in addition, of course, the ancillary data that we need to understand the different forcings. We need temperature, salinity, inorganic nutrients, and dissolved oxygen. CARIMED will follow the GLODAP philosophy and methodology, and will, although it is independent from GLODAP, it will be linked to GLODAP and eventually merge with it. Sorry. Here is the flow chart for producing CARIMED. First, we started collecting and contacting the PIs for the different cruises to be identified in the bibliography. We also searched in different public databases, or we directly contacted the PIs. So then, up to now, we have 46 cruises, which span since 1978 till 2019, the last cruise we have. Our group participated in that. They cover the different subbasins in the Mediterranean Sea, except for here this white hole in sea. I think it's Libyan waters. Each cruise is identified with an ESPO code. Is formatted as CSV file, and this original cruise file, along with the metadata containing all the information about the methodologies and quality control especially for the biogeochemical variables, will be uploaded in an interactive cruise summary table in HCI OCATS, the former CDAC. The final step is the secondary quality control procedure, which is quite a bit problematic, and it aims in identifying systematic biases in the variables, especially the carbon ones, but without removing any temporal trends in the water masses. And this is quite difficult for the Mediterranean Sea because, as you know, it is completely affected by warming, salinification, and other changes, as I commented in the introduction. So we need to get to a compromise. We need to identify layers with minimum change, as, for example, in the Levantine and the Ionian Seas, the layer 1,000 meters, where we have the eldest waters detected with transient tracers. We will study and compare the different cruise data in those layers in order to detect any systematic biases in the data. For example, in the Tyrrhenian and the Western Mediterranean, we will use the layer not that affected by the Western Mediterranean transient in here around 800 meters. At the end, we will have, like you can see, an adjustment table with all the different cruises and the different variables. You can click on there and you will find the plots for the crossover analysis and the rationale for any adjustment applied to the different variables and cruises. So right now we are doing the secondary control, and within a small group we will make the decisions for applying or not applying the corrections with a final assessment with all the carbon PIs from the different cruises. We will prepare an interactive table in OCAS with containing the original and final files for the different cruises in CC and comma formatted file, along with the ODB and MATLAB files with the product. It will be an open link in OCAS next to GLODAC, but independent, and hopefully will be published this year in Earth System Science Data. Sorry. So what we would like is that the whole oceanographic community uses CARIMED to make the best oceanography with the best data for for me, my beloved Mediterranean Sea. So thank you.
Thank you so much, Marta. It was great to hear about that exciting work with CARIMED. Our next speaker is Iris.
So can you see my screen?
Right now, it just looks like a white screen. No text has appeared. All right, now we can see your screen. Try making it full screen. This looks great, Iris.
Okay, perfect. So first I would like to thank the organizers for inviting me to contribute to this session with this webinar. And I would also like to thank the people that have helped collect the data that I will show, and there were many people involved, obviously. So I want to talk, I want to pitch this talk a little bit different. You've heard a lot about ocean acidification in the water column, big water masses, Mediterranean scale. I'm going to talk on a much smaller scale about the influence of marine vegetation and coastal CO2 dynamics. So, of course, you've all seen this graph. The CO2 concentration in the atmosphere is rising, but at the same time, we see a little bit of fluctuation, seasonal fluctuations in the rise of carbon dioxide. And this is due to temperature fluctuations and, of course, primary production. And this is where I'm heading at. The last slide was the atmospheric concentration. We can see the same actually in marine series. This is a very famous series of CO2 in the water column in the Atlantic. And here in this graph, which you can see, I don't know if you see my my pointer actually in this series, which is the open circles. You can see the CO2, which is normalized for temperature. If we normalize for temperature, we can take out the temperature effect, and we actually can talk about net biology effect. So this is a fluctuation due to the use of carbon dioxide by autotrophs that use this as a substrate to construct their bodies and primary production. So of course, there's also the influence of sea air exchange of CO2 and vertical mixing between water layers, and there's the use of nutrients as well, which changes the alkalinity a little bit. But we can say that the main bulk of the variability is due to the use of CO2 by primary producers. So if we see this also very famous scheme of the Global Carbon Project, we see that there are sources of carbon dioxide and sinks, and the sinks are the atmospheric compartment, of course the terrestrial compartment, the forest, and the sea as well. So the terrestrial forest, they fix the carbon, and due to the primary production of this forest, they cause fluctuations in the atmospheric CO2, and they fix the carbon. So a similar thing happens in the ocean, where the CO2 is transported to the deep sea by the physical pump, but also the carbon is extracted because of the biological pump, which is very similar to terrestrial forests. And the biological pump, if we talk about the open ocean, exists of a phytoplankton, small autotrophs that fix the carbon that is dissolved in the water column by photosynthesis. And of course, this is only in the upper layer where the light penetrates, and they use nutrients and carbon to actually grow. This organic material that is produced is remineralized and reused, but some of it actually is transported to the deep sea and is buried. So, and this is how some of the carbon gets transported out of this cycle. So, if we look at a more coastal environment, we don't only have the water column, we have the benthic compartment, where in most coastal areas, if not all, there is a growth of marine vegetation. And in this picture, you see seagrasses, which are very present in the Mediterranean. This is a picture of close to where I work, of a Posidonia oceanica meadow. And this marine vegetation, this benthonic vegetation, not only fixes carbon by primary production, by the use of CO2, which is during the daytime when there's light and they can photosynthesize, while at night they release the carbon dioxide and therefore cause this pattern that we saw, which you can see on a dial scale as well. So at night, release of CO2, and during the day, consumption and fixation of the carbon. So they do the same as the phytoplankton, but also because they're physical structures, they're in the way of the currents that go over the seafloor. And this slowing down of the currents enhances the retention of particles to the seafloor and enhances a flux towards the bottom and enhances carbon burial underneath the meadows. So this is true for seagrasses, but also other marine vegetation like salt marshes or mangroves, for instance, that are partly submerged. Actually, salt marshes are much better at catching particles because they're partly submerged and not fully submerged. So due to the physical structures and their influence on the flow, we also call them sea ecosystem engineers, because they change their surroundings by influencing in the hydrodynamics and increasing this particle flow to the seafloor. So underneath these meadows, the production, which is the carbon that is fixed in their structures, can get buried, but also the particles captured from the water column. So this is a difference with phytoplankton, that because they're living on a substrate and actually interfere with the currents, they remove particles and transport them to the seafloor. So the carbon that is buried underneath this meadow is actually called blue carbon. And this is a little bit a step aside from my main talk, but I really wanted to show you how important blue carbon is, how important the carbon that is fixed, that is actually buried underneath the meadows is. And this is a picture, it's very famous as well, about carbon burial rate. So this is rate, these are not carbon stocks, this is the carbon that is captured in comparison to actually the terrestrial carbon. So on the left-hand side in green, we see tropical forest, boreal forest, and temperate forest, and the burial rate of carbon underneath these structures. And on the right-hand side, we see salt marshes, mangroves, and seagrasses. So this marine vegetation is very important in actually keeping the carbon out of the atmosphere and into the soil. So this was the small step outside, because my main topic is really the CO2 dynamics. So this is a much shorter scale process than actually carbon burial and removal. If we look at this graph, which is a graph that has on the x-axis a spatial scale and on the y-axis the temporal scale, we see that there are different processes on different scales that have a different type of variability. So if we look at pH variability on a global scale, here we talk about the process of acidification. This is a really big scale, ocean basins with a downgoing linear trend. So the pH is going down every year. Then when we look at regional scales, pH variability is also caused by watershed processes, for instance, freshwater runoff, by land use change and nutrient inputs, like for instance, wastewater plants. And at the ecosystem scale, it's very important to look at the seasons which cause a lot of variability in the residence time of water, for instance, in a bay. And then the subject of this talk is on the smaller scale, on the smaller spatial scale and temporal scale. So I actually want to talk about the coastal vegetation, the habitat scale, where the metabolism of the autotrophic vegetation is causing pH fluctuations of about 0.2 units per day. So these variations are really big compared to the linear yearly trend. And this is an environment in which animals and plants are actually living. So some of these environments, to show you how big and how productive they can be, this is a slide of Arctic coastal macrophytes, so kelps. Because of the retraction of the ice, they have more light. The temperatures are going up, so they're actually migrating and expanding their territory. And these kelps can grow really big. Here you see a picture of 3 of my colleagues next to a kelp. So they are really big and very present in this kind of environments. So we went to the Arctic and we did a study we measured the pH over several days. And here you can see a graph of a 24-hour daylight period. So these are several days where the sun didn't go down. It didn't go down for us humans because it looked like it was always light. But if we look at the lower part of the graph, you can actually see that there's a lot of variability in light intensity. So there is a diurnal cycle in light intensity, so capacity for photosynthesis for the vegetation, but for the human eye, it was light all the time. So there's more light present than, for instance, temperate systems. So what we see is in the blue line that the plants, the vegetation in these sites were productive. So there was a diurnal pattern with more oxygen production during the day and less during the night. But what we see as well is because there was so much light availability and the plants were so productive, we can actually see that they deplete the carbon dioxide in the water in their surroundings. So there is a lowering trend over this week period. It was a little over a week, where we can see that the CO2 in this water mass is actually depleted and the pH is going up. So in this measurement site, which was very coastal and very shallow, yes, we can actually see that the plants are so productive that they influence the pH and cause a downward trend in carbon dioxide in the water column in this period, 24-hour period. Of course, you have to keep in mind that this was a 24-hour daylight period. In winter, when there's no light, the opposite would occur. So the plants would only respire, not be productive, and actually cause the opposite effect. So is this really due to the presence of the plant? Yes, we think so, because here we have a graph on the left-hand side where we see the correlation between the pH in the water column and the oxygen concentration in the water column in 3 different deployments. So these were 3 different days where we can actually see that they're really related. And when we look at the maximum daily pH, the daily pH reached during a day, and the radiation, the light that is actually usable for the plants for photosynthesis, we can see that this is positively correlated. So if there's more light availability during the day, the maximum daily pH in the water column is higher for this 2 types of vegetation, which was a kelp forest and filamentous algae next to it, where of course we have a little bit of interchange from the water column. This was in the higher latitudes. Of course, in the Mediterranean, we have coastal vegetation as well. We have coastal vegetation all around the world. So in the tropical regions, this is mostly mangroves, while in temperate regions, it's salt marsh and seagrass is pretty well spread. So in the Mediterranean, the most dominant vegetation is seagrass, Posidonia oceanica, which we see here on the lower graph, which is covering a lot of coastal area. I want to look at our research site specifically, which is the Balearic Islands. So this is in the middle of the Mediterranean. The Balearic Islands have a lot of seagrass meadows around them. So it's the coastal area can be very productive. So we have 2 measurement stations outside, one in the Bay of Palma and one in the National Park of Cabrera, which is a small island off the coast. So these two sites were chosen, of course, for logistic reasons, but also because the Bay of Palma is a more anthropogenically influenced site, while Cabrera is like a really pristine bay with a lot of lush seagrass, and we expected the seagrass to influence our measurements, and we really wanted to see if we could see the effect of the marine vegetation in the water column signal. So one of the buoys is anchored at 30-meter depth, and the other one at 8-meter depth, but the sensors are actually much more shallower. So when we look at the signal, which these two sensors pick up, they're both semi-pH sensors, so we're looking at pH here. What we see is that the sensor at 1 meter depth in the Bay of Palma gives a signal that doesn't have a really discernible diurnal pattern, while the sensor at 4 meter depth in the over the seagrass meadow has a very clear diurnal pattern. So here what we see in green is the light period in which we see the pH going up during the day, going down during the night. So we can actually see the separate days in this graph because there's such high productivity of the seagrass meadow that we pick up the signal in the pH signal in the water column. So in the case of a limited depth, because this station was over 8 meters of water and high metabolic activity of the meadow, like here in August, over these few days, we can see that we can actually pick up the influence of the marine vegetation in the pH signal in the water column. While on a little bit bigger scale in the Bay of Palma over a deeper station, we cannot. So, of course, this is very preliminary data. Actually, we still need to entangle all the factors in this pH signal. We need to account for fresh water runoff, but I have to tell you that in August in the Balearic Islands, there's almost no fresh water runoff because there's no rivers here, and the only water that actually fresh water is rain. So August usually is not very rainy. Of course, we need to look at nutrient input and use, primary productive production of plankton, and respiration, exchange of air, sea, carbon dioxide, and also the mixing of the vertical and lateral mixing of the water masses to evaluate how much the benthic primary production and respiration, of course, contributes to the signal that we are actually measuring these coastal systems. But I'm very positive that the benthonic primary production has a big contribution, like it has in the Arctic in 24-hour light, because at limited depth with very active vegetation. So I hope I've been able to convince you that marine vegetation influences coastal CO2 dynamics, and I thank you for your attention.
Thank you very much, Iris. I'm certainly convinced. Our next speaker is Michele Gianni, and I want to apologize. I actually skipped over him. He was supposed to be the next speaker. So Michele, mi dispiace, and I'm now making you the presenter.
Okay, thank you. Thank you for to the organization for inviting me and for organizing this interesting session. Can you see my screen?
Yes, we can see your screen, and it looks like
okay.
You'll just have to go to the top, Michele, and change the setting like we did in the beginning. Duplica. Perfect.
No, duplica.
No, this worked. This worked.
Is okay?
Yeah.
Is work? Is okay or
yeah,
not?
Go back to presentation mode like you were about to click. Yes. And go to duplica.
Yes. Okay. Now should be okay, I suppose.
Yes.
Is okay?
Mm-hmm. Go.
Okay.
Take it away.
Yeah. Okay. So I will talk about maybe about the drivers of pH and CO2 variability in the Adriatic Sea. But you can see the full screen, or is covered by something?
No, we
Okay.
see full screen. Your GoToWebinar dashboard has been hidden.
Okay. Okay, thank you. So going down, or it's not going down? It's not moving. Okay, now. Yes, so we have in the Adriatic, we are studying this semi-enclosed sea with two observational systems. One is in the north and one is in the South Adriatic, in the deepest part, where we have a buoy in these two places. So the Adriatic can be subdivided in three parts, which is the northernmost part, which is less than 50-meter depth, the middle part, and the southern part, where you have a pit that reaches down to 1,200 meters about. And you have a seal where there are the exchanges between the Adriatic and the Ionian Sea. So in this part, or in these two sites, we are measuring different components of the carbonate system and of main variables in order to characterize the water masses at different depths, but the CO2 system is measured only near the surface. So in the Adriatic, we have a lot of river discharge, and is a high contribution to the total fresh-water in the Mediterranean Sea, because about 21% of total freshwater are discharged in this small area of the Northern Adriatic Sea. And as you can see from this graph, the main river, which is the Po, deliver most of the total CO2, especially in the form, mainly in the form of bicarbonates, to the seawater. And the smaller rivers have a much smaller contribution, and as the Po River contributes for about 70% of the total export of TCO2 with respect to the other smaller rivers. So overall, if we calculate how much is a river in discharge in gigamole of carbon per year, with respect to the bulk of the TCO2 which is present in the water, in the seawater, we have that about 33% per year is coming from the rivers. So this is why it's important to have a long time series of it's important to have this time series both in different places of the Adriatic Sea. In this part, we have two sites where we are measuring the CO2 systems, which is the Mambo buoy in the Miramare protected area, and the station where we have a long time ecological research series. So this is the scheme of our buoy, and the CO2 system is measured mainly, it's minus 2 meters from the surface. And we are measuring PCO2 and pH, whereas the discrete samples, in the discrete sampling, we are measuring pH and total alkalinity, and we derive the other carbonate system by these two measurements. This is the time series from 2011 for the carbonate system. Here is represented only the pH variation, from which you can see the seasonality. There is a strong seasonality with lower pH, usually in summer, beginning of autumn, in the bottom waters, and in some cases also reaching also the surface water. So if we see which is the mean annual variation of pH is about 0.03 units of pH as an average each year. And big part of this variability of the pH is due to the thermal effect on the carbonate equilibria. And as we have in this part of the Adriatic, which is the northernmost part of the whole Mediterranean Sea, we have really a great variation during the year. We have an average of 18.5 degrees as average of variation between the winter and the summer. And here you can see the apparent oxygen utilization that is showing that the variability of, especially in the bottom waters, due to the stratification also of the system, and where we have the increase of the apparent oxygen utilization in late summer, autumn, we have also the highest decrease of pH, which is really a seasonal event. Usually below the stratified waters, so in the bottom waters, which are below the main pycnoid line, except in some cases where we have also this low oxygen water and low pH water coming to the surface. So in this case, you see that there is we had, no, sorry, I went one, I wanted to go to this one. Yes, in this case, you can see this event. Sorry, you see that here we have a continuous recording of the PCO2 and pH, and we had this very rich waters of PCO2 which came to the surface, and contemporarily also we had a very low oxygen measured by the other sensor, and which was just after a Bora blowing that brought to the surface the bottom waters during this period, which was it's the late summer. And so we had an upwelling event bringing this low oxygen and high PCO2 and low pH waters to the surface. This was a very short event that was fortunately recorded both by continuous monitoring, automatic monitoring on the buoy, and also by our discrete sampling. So this is just the recently ended mission of a sail drone, which started from Canary Islands and Capo Verde, and after 9 months mission reached the Gulf of Trieste. And here you can see the PCO2 in seawater recorded by these drones that were going only moving with wind, and they were measuring many parameters, and also the PCO2 in air and PCO2 in seawaters. And this will be interesting also for the comparison of the different sites where the CO2 system is measured in the different area of both of the Atlantic and also of the Mediterranean Sea. Here below you see a comparison with different data measured by the system, these sail drones and our buoys. In the Mediterranean, in the Adriatic Sea, we have a strong spatial variability across the gradients that from the western part, where we have the highest influence of fresh water, towards the eastern part, where this influence is much less. As you can see below in the gradient of salinity, but which reflects also a gradient of total alkalinity, total CO2, and also a gradient of pH, which is also due to the primary productivity by phytoplankton. And the relationship between alkalinity and salinity is that we have an increase of alkalinity with decreasing salinity due to the river discharge. As I showed before, they contribute to increase the alkalinity in the system. We have, if we go to try to see which is the thermal effect with respect to the biological processes, which is here represented by this TB ratios, we see that we have a thermal effect which is higher than 1, mainly in summer, whereas in other periods we have the biological effects exceed the temperature effects, and this reflects also on the fluxes of CO2 between the seawater and the atmosphere. Here we calculate the fluxes from the concentration of CO2 from the partial pressure of CO2 in air and partial pressure of CO2 in seawater, and we can see that we have mainly an influx for most of the periods, whereas in some periods, mainly during warm and stratified period, we have a CO2 efflux, which is represented by the part where the flux is higher than 0. And so the highest influx usually is during winter time, where we have a stronger cooling, which facilitates the absorption and dissolution of CO2, and where we have also high wind speed, which enhances the exchanges between from the atmosphere to the seawater. So in this slide, I show the mooring, which is in the Southern Adriatic Sea, which is moored on 1,200 meter depth, and where in the surface near at 2 meters depth, we have also the PCO2 measurements. And here are represented some data from where you can see that the maximum PCO2 is reached always during summer, when we have the highest warming of the surface seawaters, which is, as I showed before, due mainly to this temperature effect. If we look at the transit crossing the Southern Adriatic in this pit, we can detect these intermediate waters which have a high salinity and a high PCO2, and these are intermediate water of Levantine origin, which were formed in the Levantine basin, and then they moved across the Mediterranean, reaching also the Southern Adriatic Sea. We can also notice an increase of PCO2 in the bottom waters, which is due to the physical pump, mainly related to the formation of the Adriatic dense water, which flow to the bottom of the pits, and partially also they flow along the western slope out of the Adriatic basin. So this is from a modeling work made from colleagues, where they estimated that on average the Adriatic is a sink of CO2 from the atmosphere to the sea. And from this scheme, you can see which is the contribution of the Adriatic, which with the dense water, will transport also CO2 to the deep water of the Mediterranean Sea. So thank you for your attention.
Thank you very much, Michele. We are now going to hear from our very last speaker today, Naira.
Is it okay now?
Yes, we can see your screen and we could hear you. We're just waiting for your presentation to go into full screen.
Okay.
All right, now it looks excellent. We could hear you and we see it full screen. Take it away.
Okay. Hello, everybody. I will present another aspect of ocean acidification. I will show a small introduction for impact of ocean acidification in Mediterranean Sea flow economy. At the beginning, why Mediterranean Sea is important and the economy of the Mediterranean Sea is very important for us. Because it hosts about 30% of global seaborne trade by volume and about a quarter of oil traffic. It has 450 ports and terminals. It is the second largest market for cruise ships. Cultural-wise, the cultural diversity and geopolitical complexity of Mediterranean Sea show the safety and security issue. Coastal as one of the most important points to take in consideration. Coastal pressure from the higher large number of population on the coastal city and the pollution impact, resources over exploitation, which decrease the resources of fisheries and mining and oil and gas in Mediterranean, which grab to our attention that how important to study all the factors that affecting its economic aspects. In addition, it's a unique biodiversity environment. It contains 400 UNESCO sites and 236 marine protected areas. Culture of environmental healthy life. What's the blue economy sector that is important for the Mediterranean Sea? It's extraction of living resources for professional fishing, either by trawling or other industrial fishing or small-scale fishing, recreational fisheries or marine aquaculture. The second is extraction of non-living resources, such as marine mining. The third is energy production from renewable marine energy or oil and gas exploration and extraction. The fourth is land-based activities, which is the source for pollution and the coastal development. The fifth, which is very important, is transportation. Maritime transportation comes to the first position for marine economy for Mediterranean Sea, followed by tourism. How ocean acidification can impact and affect biological ecosystem. It affects biological ecosystem, and this effect on biological ecosystem goes to the rest of these 6 sectors of blue economy. It can affect biological ecosystem either by direct effect or indirect effect. For direct effect, the first point is the chemistry, carbonate chemistry, and its impact of acidification on chemistry. The impact on chemistry reduces saturation of a calcite and aragonite, which hence impacts the calcifiers of marine organisms and marine habitats, causing dissolution of the skeleton of these organisms and impacting their shells and skeletons. Also, it impacts their energy, habitat, body energy, energy balance, which affects their reproduction, growth, behavior, and survival. Also, it affects the respiration and the balance between carbon-nitrogen and carbon-phosphorus ratio, which affect all the trophic web. So, how organisms will change, how acidification will change the marine ecosystem. The ecological impact of ocean acidification will be species-specific and community-specific impact. So each organism reacts differently, and this effect can be positive or negative according to their reaction. Coral and shell builders decline, seagrass may increase and replaces corals and other organisms and other habitats in their area. For fish, become disoriented, prey loss if affect predators, potential fish catch decline. Let me start with fisheries and aquaculture and the impact of ocean acidification on fisheries and aquaculture. Fisheries and aquaculture contribute to the economy of the countries bordering this sea around the Mediterranean Sea and provide food and employment to coastal community. It employs about 600,000 people with about 4.1 billion euro of gross value added of 353,000 direct jobs created in fisheries. The fisheries and aquaculture industry in the Mediterranean Sea is the third most important blue economy sector in socio-economic terms, after tourism and maritime transport. To date, fisheries account for about 60% of the total value of the sector, while aquaculture represents about 40%. As you see in this diagram, that the landed value of the fish on the land is reached its peak during 1990 and again at the mid of 20,000. So has been declined and then after has been declined since 2006. Fisheries employment, according to GFCM data, about 220,000 fishermen are directly employed in the Mediterranean. The sector has suffered significantly decline in jobs over the past decades. In 1995, there were 377,000 fishermen in the Mediterranean. The greatest loss of employment was recorded in Croatia and Lebanon after that. Direct effect of fish and shellfish. Increasing temperature and heat wave frequency are causing stress and mortality in marine organisms, and ocean acidification is expected to worsen these effects. The impact of ocean acidification on mollusks and calcifiers is not limited to their growth and calcification, as several physiological processes are affected also by hypercapnia. Ocean acidification will affect fish growth rate, reproduction, sensation, and movement. Early life stage are more vulnerable to acidification and warming than the adult fish. Although some types of fish are able to withstand the projected increase in seawater carbon dioxide, degradation of seabed habitat, and increase in harmful algal bloom and jellyfish may adversely affect fish stock. Ocean acidification impacted the changes of trophic web. So, the abundance of marine resources, including both mollusks and fishes, are strongly dependent on the structure and functioning of the regional trophic web. Fish invasion highly increased by both climate and acidification. This diagram showed how organisms and habitats in different sea grounds can impact their growth rate and how it can decline by the ocean acidification. Coming to the maritime sectors, which is the most important one for the blue economy in the Mediterranean, most important, the highest important, or the first important sector of blue economy in the Mediterranean. It includes related port activity and has reported significant growth in the Mediterranean over the past decade. The Mediterranean records intense maritime transport of goods, energy products, and passengers. To date, it's the largest load of discharge center for the transport of oil products, about 18% of the world transport. On the Mediterranean coast, there are about 600 ports, some of which are among the most important in the world. Among the Southern Mediterranean countries, Egypt and Morocco have the largest and high number of ports. It's respectively 59 and 30 ports. Economic values and employment. The total revenue of the sector, transport service, port activities, and shipbuilding was about 7 billion euro in 2010, generating a great value added of more than 25 billion euro, about 5% of industry value worldwide. In terms of employment, it's estimated that about 550,000 jobs are directly created by this industry. How ocean acidification impacts this maritime sector? Acidification was significantly changed by fouling community composition by decreasing the calcified and increasing soft bodies organisms. Moreover, dense population of macroalgae appears at the surface of ships and underwater objects. It will also affect the rate of leaching and dissolution of toxic ions in the veins, thus decreasing fouling, and hydrolysis of colipolymers of anti-fouling coating. Because coating chemistry, temperature, pH, and flow are flow dependent. Marine fouling generates surface roughness, which increases the drag resistance of the ship moving through the water and consequently increases the consumption and emission of greenhouse gases. Heavy calcareous fouling may result in lowering panelists for more than 85%. Coming to the last sector, the last important sector, which is tourism, the second place for the Mediterranean blue economy. The Mediterranean is the world's leading tourist destination, both in terms of international and domestic tourism. In 1970, 58 million international tourist arrivals were registered in Mediterranean countries. By 2014, this number has increased to 314 million, and the region was expected to attract 355 million in 2016. Regarding tourism, how acidification impacted tourism by habitat destruction and invasion. Also for cold water coral, their acidification decreased their metabolism and growth, while body skeleton dissolves in unsaturated calcite and aragonite media. Warm water coral have reduction in growth and net calcification rate. Also, it changes the trophic level, the trophic web, as I mentioned before, and could indirectly impact the abundance and quality of the lowest trophic levels. Benthic food web in the Mediterranean are supported by the productivity of meadows of seagrasses, Posidonia oceanic, which is also impacted. All of the previous will impact tourism in the Mediterranean Sea and hence impact economy. Recommendations: it's recommended that ocean acidification should be reduced through different mitigation plans for carbon dioxide emissions. There will be a bad need to monitor ocean acidification regularly with assessment of the likely socio-economic impacts to build adaptive strategies for Mediterranean countries. Translate science into more touchable and understandable language for policymakers. So we need more socio-economic studies of ocean acidification impact on flow economy. Thank you. Hello?
Hi, thank you very much for that presentation. So at this time, I'd like to thank all of our speakers today for all of their wonderful presentations. I want to acknowledge those that have to leave. We are about 5 minutes over time, but for those who are able to stick around, I will begin asking our speakers some questions that have been posed by our audience. This also goes for our panelists. If any of you have to leave, we'd completely understand, but we'd like to get in at least one question for each of the panelists. There's a lot more questions than we have time for today, so what we're going to do is continue the conversation on the Ocean Acidification Information Exchange. So we'll copy down all the questions, type them onto a post on the OAIE, and continue the conversation there. But at this time, I'll begin asking some questions to our audience, from our audience to our panelists. So the first question comes from Libby Jewett, and this is for Patrizia. And Patrizia, when I finish asking the question, you could go ahead and unmute yourself and answer. So from Libby Jewett, from the literature review, where would you like to see future research focus? And I'm also going to expand upon that and ask you to think about, do you expect any declines in paper output due to COVID-19? And how could that kind of be mitigated so that the science in the long term doesn't suffer?
Well, thanks for the question, Libby, and also Mike. So for what I see in terms of patterns and publication, yeah, I see this slight decrease in publication already starting in 2018-19. So, and I will expect also this year from this first scan we did for 2020 that the number of publication could decrease compared to previous years. Of course, there is a relationship between publication output and funding, as expected. And also, we even did a bit of research there and looking at funding in terms of like percentages compared to GDP per country. And there is, of course, a relationship as expected. So I think in order to alleviate this issue, I think these ocean acidification hubs, I think, are very critical, these regional hubs. I think improving networking, improving collaborations, and finding synergy between different institutions, also with different capability in terms of infrastructure, I think is key. I mean, regionally, of course, it's obvious that there are some regional gaps within the Mediterranean. As I mentioned, most of the publication output and also biological study time series are in the northern part, in European country, mainly in the northwestern Mediterranean. So I think we need to explore much more other regions, other systems, more like North Africa, for example, or Eastern Mediterranean. I think there is a lack of studies there. And I think to alleviate that, I think networking can be key. Also, yeah, negotiating hopefully more fundings at the national and international levels. I think it's very important. And of course, I mean, as also Naira mentioned, from the societal point of view, social science studies are key. And we really still, I mean, we started some years ago to say this, the importance of like interaction between social and natural sciences. But I think it's still, there is a lot of work to do in this direction and working also at the local and more local level for linking needs of the social needs and peculiarity or characteristic at the different temporal and also area scales.
Thank you, Patrizia, for that response. The next question is for Marta from Bronte Tilbrook. Bronte writes, Marta, CARIMED is a great initiative. Will you provide calculated values of pH and carbonate mineral saturation states with the final data set, or is the data set only going to include measured values?
Okay. Yeah, following GLODAP in the product, not in the original files, we will provide all the calculated values for different carbon species. In situ values, probably.
Excellent, thank you. All right, I actually have a question for Majd. I was wondering if the thickness of a coccolithophore's shell influences its digestibility for planktivorous organisms like bivalves. So would a bivalve be more likely to eat and digest a coccolithophore with a thinner shell, or does that not have an influence?
Hi again. I don't think that these bivalves do anything for the coccolithophores. No.
Okay, thank you very much. Our next question is for Iris, and this comes from Frederick Gazeau. And it is, did you correct for any potential temperature changes during the day?
Fred, this is very preliminary data. I will. It's corrected, it's at the constant salinity, but no, it's not corrected for temperature yet. But the temperature is very similar